everyone. My name is Martin Káčerik. I'm actually Slovak, not Czech, but that's a minor detail. Here in the US, anyway. So, yeah, that's all right. So let me present to you our work we did together with my supervisor, Jiří Bittner. And there's quite a few of terms in our title, so let's address them one by one. I believe everyone here already heard something about ray tracing. So just briefly, at the core of ray tracing methods, there lies this task of evaluating the intersection between the ray and an object in a scene. And contemporary scenes have millions of objects to test, and we often like to trace billions of rays. So if we do this naively, this quickly gets out of hand. So to address this, acceleration structures were introduced to ray tracing, and one such structure is a BVH. We already heard today something. So the idea of a BVH is simple. If we want to test an intersection with the scene, we build a BVH for the scene and use it as a proxy for the test. So here we quickly reject this ray after one test, and if we are actually to hit something, we proceed down the hierarchy until we reach the leaf node where we test just the subset of the geometry of the whole scene. Yeah, and there is one complicated task in this involved, and that is the BVH construction, or the question how to optimally arrange these bounding volumes to a hierarchy. And this is a hard problem. In fact, it is believed to be NP hard, so we could use some guiding through this process. And so we use heuristics, and one widely used heuristic is SAH heuristic, which means surface area heuristic, and it states following: under certain preconditions, this is true that the probability of hitting a child node contained in a parent node equals the ratio of their surface areas. This is nice because we can often easily compute the surface area during the construction process, but unfortunately the preconditions I mentioned are almost always violated in the process. So this is just a heuristic, but it still correlates reasonably well enough with the optimal solution, and we still use it. So now let's address the bounding volumes we can use for our BVH. There's a few options, all extensively researched throughout the years, and the most used option, or the most used bounding volume, is actually an axis-aligned bounding box, because it offers a favorable trade-off between the performance and memory requirements. However, it is known that axis-aligned bounding boxes provide a rather poor fit to a certain kind of geometries, like slanted triangles, and they create a box with a lot of empty space. And to this end, these more complex structures were also extensively researched. And here I will mention two works from the last year by Vicas et al. And Sabino et al. And they have two things in common, or maybe more than two, but I will mention two. So both of these works produce a hierarchy of approximate OBBs, or oriented bounding boxes. And both, during the construction process, use an intermediate representation for the bounding volume in a form of k-DOP, or discrete orientation polytope. So we wanted to take a closer look and better understand these k-DOPs, and that's what we did. So let me show you some k-DOPs and what they actually are. They certainly look cool, and you can clearly see that they provide a tighter fit to the underlying geometry. But what are they? So from a mathematical standpoint, a polytope, or k-polytope, is an n-dimensional object defined as an intersection of k hyperplanes. And for our specialized 3D use case, it's actually a convex polyhedron defined by k plane, or intersection of k planes. And the discrete orientation part means that the normals for these planes come from a predefined set. And we choose our normals in this set. So with an example, if we, for example, use the following N6 set of normals, we end up with a 6-DOP, which is actually an axis-aligned bounding box, which is a specialization of a general k-DOP. And if we proceed to extend this set by 8 additional normals, in this case, these normals, if you imagine a unit cube, these are the vertices of a unit cube. So if we use these normals, we end up with a 14-DOP of of this shape, we can informally define it as an axis or describe it as an axis-like bounding box with cut corners. And this is the k-DOP we actually focus the most in our work. So, as we learned a few moments ago, it would be beneficial to know how to compute the surface area of a bounding volume for the construction of the BVH. And for a polytope, this is defined as a sum of surface area of its facets, which really is easy enough for an axis-line bounding box to compute. But what can we do with this? So these 14 DOPs, or even more complicated polytopes, we have a mathematical apparatus to deal with this. But from a computational standpoint, it is really, really expensive. However, our 3D 14 DOP is a lot more constrained than a general polytope. So perhaps we can do better. So we propose a following geometry-based algorithm. If you remember my informal description of a 14 DOP, that is just an axis-line bounding box with cut corners, perhaps we can approach the surface area computation the same. So we start with the surface area of an axis-line bounding box and proceed to cut some corners. How this might look like? So we have an AABB and we cut one corner. This means we simply subtract the 3 triangles of this corner from the area of the AABB and add the newly formed face. And we end up with a polytope of this shape, and we know its surface area. If we continue to do this and subtract another corner, and we repeat the process, we add the newly formed face, we end up with a polytope of this shape, but perhaps you can see a problem there. And this problem is this overlap region that forms by the overlap that is formed by the 2 corners that overlap. So to get the correct surface area of this polytope, we have to compensate for each possible overlap region, and there happens to be 12 in the 14 DOP. So the full derivation of this formula is in the paper. I will not go into much more details here, but I will mention this. Both the surface area of the corner and these overlaps, these are the functions of this variable d, which is actually a distance of a cutting plane from the vertex or corresponding vertex of the AABB. It fits to a few lines of code, and it is 1 order of magnitude slower than computation of AABB surface area, but it is 3 orders of magnitude faster than performing vertex enumeration over the same 14 DOP, which is nice. So now, with this knowledge, let's build some BVHs. In our paper, we propose 3 methods for BVH construction with 14 DOPs, and I will go through them one by one. The simplest one is a transformation of an existing ABB hierarchy to a new 14 DOP hierarchy. This can be done in one bottom-up pass, which is actually quite simple. So imagine we have an existing hierarchy. We start by fitting its leaf nodes. In this case, we fit 14 DOPs for the leaf nodes, and proceed to merge upwards until we reach the root of the hierarchy. And we end up with a hierarchy of 14 DOPs with the topology of the tree optimized by the previous builder, likely for the AABBs. The next algorithm we tried is actually constructing the 14 DOP BVH from scratch using the block algorithm, which we already had extensive introduction today. So just briefly. Block or parallel locally ordered clustering is a bottom-up algorithm. So we start the construction from the leaves. We feed 14 DOPs for the leaves. We order them along the space filling curve and start the merging, the iterative merging process. So the candidates for the merge are evaluated by a distance function. And this distance function, in our case, is a surface area of 14 DOPs, or the function I presented to you a few moments ago. So when we find the best possible candidates by minimizing the value of their distance, we merge them, and we proceed to iterate until, again, we reach the root. And in this case, we end up with a hierarchy of 14 DOPs, but unlike the previous case, its topology is optimized for these 14 DOPs and is likely different for the same scene than the previous method. And the last 14 DOP the 14-DOP BVH algorithm I'd like to present to you is based on a previous work of Vitsas et al. That I already mentioned. And this is the transformation of an existing 14-DOP hierarchy to a new approximate OBB hierarchy. So this parallel D-tetrahedron OBB algorithm is quite involved. I will not describe it in details, but the idea is similar to our first algorithm. You have an existing hierarchy, you apply this algorithm, and you end up with another hierarchy, which in this case, again, the topology of the hierarchy is optimized by the previous builder, and the new bounding volumes, in this case OBBs, are contained in the nodes. So this was the third algorithm. And before I get to some results, I'd like to share with you one low-level detail regarding the 14-DOP intersection test. So we use branchless slab-based test, similar to what is used to intersect ABBs. So for an ABB case, imagine we have, let's say, a BVH node with this binary layout. We fetch the node, and we proceed to test the slabs. In this case, XYZ or 0, 1, 2. If we extend this in a straightforward manner for 14 DOPs, we fetch the larger node made of 14 DOPs, and we, in this case, test 7 slabs. So if you look at this, you can see that to process a 14 DOP node, we deal with double the amount of memory with this layout, and more than double the amount of computation. And this was also recognized in the past work of on k-DOPs by Klosowski in '98, who proposed the following early exit idea. So in the slab-based test, when you fail one slab test, you already failed the whole test of the intersection, or the whole intersection test. And this is perfectly reasonable to do in a serial computation model. However, in our GPU implementation, it would be difficult to get any meaningful improvement because of the divergent flow this would introduce. So to get at least something from this early exit idea, we propose following approach. We split the memory layout of our 14-DOP nodes into 2 parts. In the actual BVH, we store only the AABB part, which in the case of 14 DOPs is implicitly present there. And we store the rest of the 14 DOP data in an adjacent buffer. And with this, we can proceed with the intersection test in this manner. We fetch the node, we perform the AABB's slab-based test, and we can ask for an early exit. And if we fail here, we missed the AABB, we can reject the test and save at least on the fetch of the data, of the rest of the data. And if we pass the test, we simply fetch the data and proceed with the k-DOP intersection test. And with this structure of an intersection test, we came with another condition for an early exit, and that is based on the following idea. So if you introduce more and more constraining planes into your polytope, we have so you have an ABB which has 6 constraining planes, 14 DOP has 14, and the more planes you introduce, it is more the greater the probability they become redundant. So they do not contribute to the final shape of the object, or they contribute minimally. An extreme case for this is if you imagine an axis-aligned bounding box. Its k-DOP is actually an axis-aligned bounding box, and all 8 additional planes are redundant. So to combat this a bit, we introduced something we call a use k-DOP flag that is pre-computed during the construction and storing the metadata. And is evaluated based on the threshold alpha. And threshold alpha is the minimal necessary surface area reduction introduced by the k-DOP to take k-DOP into consideration. So we set a default value of minimal surface area reduction at least 25%, and we use this during the early exit test as well. So we can decide to reject the actual 14 DOP test during the intersection test. So Now let's take a look on some results. We implemented our ideas in a C++ framework with Vulkan, both with both BVH construction and traversal on a GPU. So here is the comparison of our first two methods. The orange one is the transformation of existing ABB hierarchy to an k-DOP hierarchy, and the teal one, or cyan one, is the construction of a DOP hierarchy from scratch. What are we actually looking at here are two k-DOP hierarchies, and the orange one was optimized, has optimized topology for ABBs, and the blue one, or the teal one, has optimized hierarchy for the 14 DOPs. So, and we compare them relatively to an ABB hierarchy built by the PLOC algorithm. So we can clearly see that, as expected, our k-DOPs are a little bit more expensive to compute. But if you remember that the surface area computation is actually 10 times slower compared to ABB surface area computation, it turns out well hidden in the process. So, and on the right, there is a comparison of the actual performance of the BVH, in this case on secondary arrays. So, often, or almost always, these k-DOP hierarchies perform better, at least on the tested scenes, than the ABB hierarchy, with one exception of San Miguel scene. This scene is quite well axis aligned, and thus the additional planes in the 14 DOP are actually to the detriment of the traversal. However, especially two scenes which you probably would expect to do well, our 14 DOPs are hairball and sheep, where it's like a hair structure and a fur structure in the scene. And in these cases, the k-DOP hierarchies provide a nice speed up on the traversal. And on this slide, I compare the third approach to k-DOP hierarchy, which is a transformation of an existing k-DOP hierarchy to an OBBs in a fashion introduced by Vitzes in his work. And we compare it to an orange, or the original work. And again, this is similar to the previous slide. So you can think of the orange BVHs as optimized with ABBs, or the topology is optimized with ABBs, and the teal ones are optimized with k-DOPs. And in both cases, the bounding volume used for the test is an oriented bounding box. So in general, these are quite slower compared to raw 14 DOPs. And for the most part, they perform in the similar ballpark of improvement. In the case of San Miguel, they perform even worse due to the alliedness of the scene, and with one notable exception, that is the sheep scene. So the dense tessellation of the fur in this scene is exceptionally favorable for the OBBs in this case. So to conclude, I presented to you following contributions from our work. To allow a construction of k-DOP BVHs, we introduced a fast and precise algorithm to compute the 14 DOP surface area, and we integrated it with the PLOC builder. To allow efficient traversal of this hierarchy, we proposed an early exit test and use k-DOP flag, which is also used for an early exit test, and these both are enabled by our split memory layout for the node. And I presented to you results of our 14 DOP hierarchies, which are slower to build than ABB hierarchies as expected, but when they work better. And this is often, to be honest. This all, of course, for the additional price, for the price of additional memory. And I also presented to you that these 14 DOP optimized topologies can be beneficial in the construction of OBB trees. So, one last thing, I'm currently looking for an internship, so if you feel like I could contribute to anything you do, please let me know. And with that, I'd like to end my talk, and thank you for your attention.
Do we have some questions?
What fraction of the nodes for your different test models use k-DOP flag?
Yeah, this is...
Can you repeat the question, please?
Yes, the question is, what fraction of the nodes actually use k-DOP flag to reject or to apply the early exit? Yeah, I don't have the data. I actually plotted this, and this is highly scene dependent, so it's difficult to predict. But you can say it roughly correlates with the value of the threshold. That's the best, best.
For the default threshold of 0.75, do you recall what fraction you got for any of those models?
Well, I can't provide you with numbers, but it would be between 0.7 and 0.8 nodes.
70
I
to
believe
90% use the
70 to 80, but it's just the rough approximation. I'm not entirely sure.
Way in the back.
I can yell, if anyone can hear me. So the k-DOP is basically the intersection of a queue and the octahedron in the middle of it. Did you actually investigate what the performance of just the octahedron was? You don't bother doing exercise.
Yeah, I did this early when I started with this work. And it was so bad in that case that I didn't continue to track this. Maybe with some optimizations I introduced, it would actually work. But yeah, these octahedrons tend to be quite larger in terms of surface area, and so the BVHs didn't really work well. It worked, it ran, but it was slower.
Hey, great talk. Would it make sense to use the k-DOPs only at the leaf level of the BVH? Have you tried?
Excuse me, when?
The k-DOPs, use them only at the leaf level of the BVH, only at the lowest level. Would it provide enough culling efficiency?
So we addressed this in a paper, in a discussion. It is one of the insights, actually, that I probably should have mentioned. But the fact is that not really, because especially in the combination with OBBs, it turns out that OBBs are much better in the leaf nodes. And on the other hand, the k-DOPs perform actually much better in the internal nodes of the BVH. So yeah, so for the leaf nodes, typically OBBs provide much greater reduction of surface area, at least in comparison with ABBs. And as I mentioned, in the internal nodes, k-DOPs provide better reduction than OBBs.
Great, let's stay on time, and let's thank all three of our speakers for getting us off to a rousing start.